Alright, let's start with chapter 3, parametric equations called geometry in the xy coordinate plane, whatever it's called. It's alright, it's okay. Basically, you're used to having functions or curves or equations of lines in the form of y being a function of x, right? So y equals x squared means that y is a function of x. But sometimes there are more complex curves, or maybe certain types of movement of particles that is more interesting or perhaps more useful to model them separately. So x and y are themselves a function of a different parameter. So for instance, we could have this equation where the position on the x-axis is maybe a function of time, so x equals 2t, and then the position on the y-axis is itself a function of t. So we are modeling the x and the y positions differently. Now these are the parametric equations, parametrics because they depend on a parameter, t, and we need to define, typically you find this, they are defined for a certain range of values of that parameter. Now the easy thing to do is to convert this into the Cartesian equation. The Cartesian equation is the one you know, so y as a function of x. And it's just manipulate the algebra, substitute, and do that sort of thing. So if I wanted to find the Cartesian equation, all I had to do was write t as x over 2 from the first equation, and then sub it into the second one. So y equals x squared over 4, and that's it. That's the Cartesian equation. So literally a little bit of algebra. Now points to note, okay, and this is, I'm doing it the other way around from the book because it makes more sense to me. I'm going to try to link the domain and range of the parametric equations with the domain and range of the Cartesian equation. So the range of this parametric equation, the range, remember the range are the values you get out. So the range of this function is the domain of the Cartesian, okay? Because the values that I get out of this are the ones that I input here. So the range of x is the domain of the Cartesian, and equally the range of this function here is the range of the Cartesian. If you want a bit more formulaic, like they do in the book, so in general terms, if x is a function of a parameter and y is a function of another parameter and y is a function of x, these are the parametric equations, this is the Cartesian equation, then I can say that the range of x is the domain of the Cartesian, and the range, well, let's not call it x, let's call it the function, and that the range of the q function is the range of the Cartesian. Alright, so if I link these notions back to my example here, what would be the domain of the Cartesian equation? Well, the domain of the Cartesian equation is the range of the x function. So the range of the x function goes from, t goes from -3 to 3, so the x function is going to go from -6 to 6. So the domain of c is from -6 less than x to 6, and the range of the Cartesian, the range of the Cartesian equation, the possible values of y's, is the range of the y function. So the range of the y function is going to go from -3 squared is 9. 3 squared is also 9. But what's happening there? I need to think a little bit about it. Actually, the lowest value is going to be when t is 0. So when t is 0, y is 0. This y is always going to be positive because it's just a parabola. So the range of c is going to be from 0 less than or equal to y less than or equal to, actually, no, it can be 0, but it is not going to be 9. And that is example number 1 of parametric equations, how they link to the Cartesian, and how the domain and range of the Cartesian equation is related to the parametric equations. Let's do one more example, perhaps a bit more complicated, and that'll be the first chunk of the chapter done. Okay, and here we are with a slightly more complicated example, but again, it's just algebra manipulation. Here I've got my two parametric equations where x is a function of the log of t plus 3 and y is a function of 1 over t plus 5, with t being strictly greater than minus 2. And there's two questions they're going to ask me, two things I'm going to try to answer and take it from there. Number 1, find the Cartesian equation, and number 2, find the range of the Cartesian equation. Just like we did before, we substitute, what's the word I'm looking for? We make t the subject of the x and substitute into the parametric for y. There you go. So here, if I take the first equation, then e to the x is going to equal t plus 3, therefore t is e to the x minus 3, and I substitute that into there, so y equals 1 over e to the x minus 3 plus 5 is e to the x plus 2, and that is my Cartesian equation sorted. End of story. And x has to be greater than 0 because from the parametric equation the lowest value of x is going to be the log of 1, and we know the log of 1 is 0, or we should remember that. So that's why our domain is from x greater than 0. And now I need to look at the range. What's going to be the range of the Cartesian equation? Well, let's think about it for a second. As x has to be greater than 0, as x goes to infinity, 1 over e to infinity plus 2, that's just going to collapse to 0. So 0 is going to be one of the bounds of my range. And the other lowest, and when x is 0, so I'm exploring, my range goes from, my domain goes from 0 to positive infinity. I've explored what happens at positive infinity. This collapses to 0. What's going to happen at 0? E to the 0 is 1 plus 1/3. So that's it. So the range of the function goes from 1/3. The range is going to go from 0 to 1/3. Okay, I've just explored. That's the domain. So explore what happens at the extremes of the domain. That's the range from 0 to 1/3. 0 not being included there. And that is it. That is just the introduction to parametric equations. We will bring trig identities, because why not, later, but for now this is it. Thank you.